Hey Robert, great to have you back. We've been talking about writing clean code. I've got a couple of examples here that highlight the importance of well-designed functions.
Cool, let's dive in. These examples are perfect to illustrate the point. The first function is quite convoluted. It's hard to quickly see its purpose.
Exactly. It's hard to tell what it does at a glance.
Yeah, it's buried in lots of detail. That's a classic sign of a function that's too complex.
So, how do we fix it?
Well, you extract the key parts into smaller, more manageable functions. You give them good names that clearly reflect their purpose, simplifying the overall design. See how listing 3 to 2 did this. It does a lot less, but it's really easy to see what it does.
That's amazing. So the render page with setups and teardowns is doing less, but its intent is so much clearer.
Exactly. It's a different abstraction level, and that makes all the difference. It becomes easier to understand because it has a higher level purpose. The intent of the function immediately jumps out.
That's brilliant. So, why is clarity so important?
Clarity saves time and effort. It's a lot easier for developers, and anyone, to read and understand code that is well structured. Imagine trying to debug code with a bunch of nested if statements.
So, is there a rule of thumb for function length or complexity?
Not really. The key is to keep functions focused on a single well-defined task. It helps maintainability.
So, just breaking functions into smaller pieces works?
Mostly, yes. It also helps with code reuse. If the tasks have similar intent, you can extract them into reusable helper functions.
That's very insightful. I see the value of keeping functions short and clean.
And using good names. If you name things clearly, the code almost writes itself.
Absolutely. Makes so much sense. Thanks, Robert. So, Robert, you've said that short functions are key to clean code. But how short is short? A couple of lines?
Chuckles, well, Andrew, the book's author really emphasizes that small functions are usually better. Think about it like this. If you need more than, say, a screen full of code in one function, maybe it's time to break it down. Modern editors let you see a lot more, but that doesn't mean you should write code that overflows a screen in today's editors.
So, you're suggesting functions should be more about a logical and maintainable level of scope, not just lines of code?
Precisely. And the author has great examples. This 30-ish line function, that's more of an idea than a specific rule.
But what about complex algorithms? Couldn't a single, very long function encapsulate a complex task more elegantly?
Maybe, but more often than not, complex logic gets harder to follow. Sometimes, the author argues that a long function just masks the underlying complexity, making it harder to debug and maintain.
Right. But how can you practically decide when to break a function down, though?
You need to be mindful of the logic and actions. If there's a logical block of activity, that could be a function. The example, render page with setups and teardowns, illustrates a clear and useful separation of concerns.
So a single, well-named function encapsulates a logical block, not just a bunch of lines.
That's the key, Andrew. Maintainability and readability trump just saving a few keystrokes.
Are there any exceptions where longer functions are okay?
Well, extremely intricate algorithms might justify a longer function, but often you can break it down into smaller and manageable logic units. It depends on the nature of the logic.
Thanks, Robert. This has been really helpful.
You're welcome, Andrew. It's about achieving balance. And it's worth it for your future self when you look at the code.
Okay, Robert. So we've been talking about writing clean code, and now you're talking about this single responsibility principle. This one thing. How do we really know what one thing is? It seems pretty vague to me.
Chuckles, it is a bit vague, Andrew, but that's the beauty, or maybe the frustration of it. There's no magic number. It's about the level of abstraction. Think of it like building with Lego bricks. You don't want a huge, multifaceted creation all in one brick, right? It's much better to divide it into smaller, more specialized bricks.
So, if a function has too many different tasks, it's not adhering to this principle?
Exactly. Look at listing 3 to 1. It does way more than simply rendering a page, right? It's fetching, searching, rendering, and appending things. That's just too much for a single function. That's many levels of abstraction inside that one little function.
Got it. What about a function that looks like it does only one thing, but in reality, it's got hidden dependencies or subtasks?
Precisely. Listing 3 to 3 seems simple, but it's determining if it's a test page, including setup/teardowns, and rendering the page. 3 distinct responsibilities. To really test if a function is adhering to SRP, see if you can extract another function without rewriting the existing functionality.
So we extract includes setups and teardowns, but that doesn't change the level of abstraction.
Bingo! That's the crucial point. It just restates the code, doesn't simplify it, so we know listing 3 to 3 is doing multiple things at different abstraction levels.
So, how do we fix it? How do we refactor these functions with multiple responsibilities?
You break them down. Extract smaller, more focused functions. If we're rendering a test page, we can have one function for the setups and teardowns, one to check for the test page status, and keep our rendering function clean.
Interesting. Makes sense. So, what's the real-world example of this in our code?
We need to see the code. But the real impact of this principle is in maintainability and testability. Imagine a system with a massive function that handles user registration, account verification, and email sending all at once. Fixing a bug in the middle becomes difficult, right? It's a maintenance nightmare.
Absolutely. Hey Robert, we've been talking about writing clean code, and it seems like a really important aspect is making sure our functions don't try to do too much, right?
Absolutely, Andrew. A well-structured function is a cornerstone of readable and maintainable code. You know, if a function gets too big, it's like a Swiss Army knife. It does too many different things. It quickly becomes hard to understand and troubleshoot.
So, what exactly do you mean by too much?
Consider listing 4.7's generate primes function. It's splitting into declarations, initializations, and the sieve. That right there suggests it's doing 3 things. A function that does only one logical operation is easier to comprehend.
Okay, so a single responsibility. But how do we practically determine that? Is there a hard and fast rule?
No hard and fast rules. It's more about good judgment and understanding the function's intent. A good rule of thumb is if you can concisely describe the function in one sentence, you're probably on the right track.
But what about functions that seem complex? Like, maybe one that calculates something pretty complicated.
That's where experience comes in. Sometimes, a seemingly complex task can be broken into smaller, more manageable functions, each handling one focused part of the calculation. Makes the overall code more modular and readable.
That makes sense. Breaking down big problems into smaller parts. Like building with Lego blocks?
Exactly. Each Lego block has a specific function, and when you put them together, you get a larger, more complex creation, but you know exactly what each block does.
Wow, that's helpful. Thanks, Robert.
You're welcome. Writing clean code is a journey.
Yeah, and like you said, it's not always straightforward.
Exactly. It's a skill that improves with practice. Experience in analyzing the logic.
Very cool. Robert, you've been talking about writing clean code, and it seems like a lot of it boils down to making code more readable. What's this step-down rule you mentioned?
Yeah, it's about organizing your functions in a way that mirrors a top-down narrative. Imagine writing a set of instructions. You'd explain the overall goal first, then go into the specific steps. Your functions should do the same.
So each function essentially builds on the last, one level of abstraction at a time?
Exactly. Each function tells the next function do this, and the next tells the one after that do that, etc. It's like a story unfolding.
That sounds nice, but it's a lot to maintain, right?
It is. Some might argue this can make code overly verbose, like a really wordy story.
But it's easier to understand?
Absolutely. You're following the logical flow of the program more directly, and that significantly enhances code clarity.
Like a TO paragraph? Sounds somewhat rigid. You see, I often find functions do multiple things to improve performance.
That's a common tension. There's a trade-off between readability and performance. Think about it. A function that does only one thing is more easily reused or tested.
But what if the single action involves multiple steps?
Well, the single thing principle is key. Sometimes you need to break down a complex task into smaller, more manageable functions.
How can we keep those multiple tasks in one function manageable?
Use intermediate, helper functions within the overall function. Each helper is still on the same level of abstraction, but they support the broader function.
Okay, so a helper function is more like a support character in your story?
Exactly. You maintain the level of abstraction while allowing for efficiency. We have code examples. You can check them out.
I see. Thanks for explaining.
You're welcome.
Okay, Robert, let's talk about switch statements. You mentioned they're problematic, but when are they actually bad?
Well, Andrew, consider a payroll system. Imagine a switch statement handling different employee types: commissioned, hourly, salaried. It quickly gets large and unwieldy.
So it violates the single responsibility principle?
Exactly. One function should ideally only do one thing. This function is doing multiple calculations based on the employee type. That's a code smell.
But isn't it just a simple decision-making structure?
It is, but the problem escalates. If we have a new type of employee, we have to modify this function. That violates the open/closed principle.
So, polymorphism is the solution?
Yes. Imagine creating separate classes, like commissioned employee, hourly employee, etc., and then using a factory pattern to create the correct instance based on the employee type.
Wait a minute. Could you give an example of a situation where a switch would be fine?
Sure. A simple menu-driven program. The menu might only have a few options. A switch might be fine. A switch in a lower-level class hidden from the rest of the system, if the number of cases is small and it's used only once. That is part of the rule of thumb.
Gotcha. So, the key is making that switch statement private?
Yeah, encapsulate it in a factory class. Then other parts of your system just ask for the employee, and the factory handles the creation.
Okay, but what if there's something specific that this particular employee type does? If it needs a unique method?
You'd add that method to the appropriate employee class, making the whole thing scalable and maintainable.
So what about the performance implications?
If the creation is done once, and the calls to the classes are frequent, there's potentially a small performance hit. But in most cases, the readability and maintainability outweigh the slight performance trade-off for scalability.
That makes a lot of sense. Thank you for the explanation, Robert.
You're welcome, Andrew. Let me know if you have any more questions.
So, Rob, you're saying functions should ideally be as argument-light as possible. Like nihilatic, monadic, dyadic. Is that a hard and fast rule?
Well, Andrew, it's more of a guideline. Think of a recipe. A simple dish, just one ingredient, is easier to understand and execute. Adding more ingredients, arguments, makes it more complex, right? With more ingredients, you have to worry about proportions, timing, and interactions.
So, you're saying fewer arguments equal better clarity?
Exactly. Imagine a function with 5 or 6 arguments. Testing every possible combination. That's a lot of work, right? And when you read the code, you have to keep track of all those arguments each time. It can make understanding the function's purpose harder, too.
But what about, situations where you truly need a bunch of data?
There are situations. Sometimes, there's just no escaping polyadic functions. But those situations are usually well justified. Think carefully if there's a better way to restructure the data to make it easier.
So, if a function is already written with many arguments, how do you tackle that without massive refactoring?
Often, you can look at the function's inputs. If there are multiple logical actions, try breaking those into separate functions, each with fewer arguments. Or, use classes and methods to encapsulate relevant data and operations, reducing the argument burden on the functions.
Interesting. How can you tell if a function has too many arguments in the first place?
A good way to start is looking for arguments that are not needed for the core purpose of the function. Sometimes it's possible to merge inputs into objects or parameters.
You're saying it's not just about how many arguments, it's also what they are, right?
Precisely. Good names, well-defined objects, and an overall clear structure are crucial to maintain a clear understanding, even with more involved functions.
Ah, this is making sense. Thanks, Rob. Super helpful. Robert, you've got a great point about flag arguments. They seem like a quick fix, but they really make code a mess. Can you explain why that is?
Absolutely. Flags muddle the function's intent. Imagine a function designed to render something, but now has to check a flag to figure out what to render. That's two things in one function. Now the code's harder to read and maintain.
So, Splitting the function seems like the better choice.
Exactly. Separate functions for rendering a full suite or a single test would be much clearer. It makes the code's intent obvious.
But what about cases where the caller already has the flag? How do we deal with those legacy systems?
You know, it's a common situation. Ideally, we'd refactor the callers too. In many situations, the best choice is to refactor everything at once, to reduce future maintenance headaches. But that's often not possible.
So, are there any legitimate uses for flags?
Well, sometimes flags are a way to implement different states. But even then, they can often be replaced with other methods.
So there's no good situation for a flag?
Not really, if you can avoid them. If the caller is passing it though, at least do the right thing and isolate the functionality.
Can you give me an example?
Sure.
Instead of A-Funktion render, boolean is suite. Use render for suite, or render for singletist.
Much clearer now.
Right? So better to create multiple functions. Makes so much sense.
Exactly. And you can even add additional logic to prevent errors. That is much clearer in smaller, dedicated functions.
Thanks for the insights. This helps a lot.
Glad to help. Always best to strive for cleaner code.
Makes me think, how do we judge a function's complexity? Is there a rule of thumb?
Yes, there's the single responsibility principle. A function should ideally do just one thing.
That's a helpful starting point. So, a function with multiple responsibilities needs to be broken down.
Exactly. You know, good code is ultimately about making the code easier for others to read and maintain.
Makes sense. Thanks, Robert. Hey, Robert, we've been talking about clean code and how to write it effectively. This try thing, it seems harder to understand than functions with just 2 inputs. Why is that?
Yeah, definitely harder to digest. Think of it like trying to follow a complex instruction. 3 arguments mean more potential interactions and ordering issues.
So, the example of assert equals, that's a common one, is tripping me up.
Precisely. The message argument is often a red herring. We often forget it's meant to explain the why, not the specifics of the comparison.
So, what's the problem here?
The order is crucial to the comparison. You want to ask, why was this value expected compared to the actual outcome?
Makes sense. You know, sometimes in production code, it can be tough to keep track of things.
Exactly. The human brain isn't wired for so many moving parts. This can lead to errors and confusion when we look back at the code.
So, all triads are bad then? Is there ever a legitimate use case?
Not necessarily. Sometimes, the triad is necessary. Like comparing a floating point number. Here, the context matters. See assert equals 1.0 amount 0.001 is actually okay because it emphasizes the tolerance of floating point values. You're not looking for exact equality, but an approximate one, within that specified tolerance.
Oh, I see. So the context of what we're testing helps determine if it's problematic.
Right. Careful design and clear documentation are key. If you can explain the reasoning in a comment.
That's helpful. So, good triads are possible. Just need to be mindful of the cognitive load.
Exactly. Well-designed triads are manageable. Poorly designed ones become debugging nightmares.
That's really valuable insight. Thanks, Robert.
You're welcome, Andrew. Now, let's move on to...
So, Robert, you've been talking about clean code, and it seems like good function names are a crucial part of that. Can you elaborate on why choosing the right names matters so much?
Absolutely. Imagine a function buried deep in code. Its only identifier is a single letter or acronym. Tracking down that function's purpose becomes a real chore. Clear names, like right field, or even calculate total cost, are the key to understanding intent at a glance.
Okay, I understand that. But right field sounds pretty specific. What about functions with more abstract or general purpose? Does the same principle apply?
Absolutely. Using verbs for actions and nouns for entities, like write for writing something and field for the thing being written into a field, is powerful. Calculate total cost gives us the action and the noun, making the function's goal crystal clear.
So, keyword names like assert expected equals actual make it much easier to understand what the function does, even with multiple arguments?
Precisely. The name itself tells you what the function expects, the order in which it receives data, and what the function's intended behavior is. You don't have to wade through code to figure out what's going on.
But sometimes, isn't it excessive? What about less verbose names like calculate?
A good rule of thumb is to favor readability and maintainability over brevity.
Interesting. Give me an example. Is calculate inventory value a better option than calc NVVal?
Absolutely. While brevity might be a little faster, the explicit description makes the intent clear, especially for someone who is not familiar with the program or is reviewing it. The increased readability has a lot more benefit.
Got it. So, clear function names really increase maintainability?
Absolutely. They significantly decrease the time it takes to understand, debug, and modify.
Thanks, Robert. This makes sense. What do you suggest if it's something simpler like getting an ID?
Sure, getID would be fine. We want the naming scheme to be expressive, but we don't want to overuse it. Every situation is unique.
Makes sense. Thanks, Robert. Hey, Robert, great to have you back. So, we've been talking about clean code, and today we're focusing on these sneaky side effects. Can you give us a quick overview?
Sure, Andrew. Side effects are like hidden actions a function performs that aren't immediately apparent from its name or purpose. Imagine a function designed to check a password, but it also secretly initializes a session. That's a side effect.
Whoa, that sounds sneaky. How does that lead to problems?
It creates these things called temporal couplings, where the order of calls becomes crucial. If you call the password checking function out of order, or at an unexpected time, you might lose important session data. So you have a temporal coupling of the password check function and the session initialization. They must happen in a precise order.
Makes sense. So, the problem isn't just the hidden action, but the implied order it creates?
Exactly. The function's name checkPassword suggests nothing about initializing a session. A developer calling it would assume it doesn't have any side effects on the session.
So, how do we prevent this? Better names, you say?
Precisely. Calling it checkPassword and initialize session might be cumbersome, but it's clearer. It directly reflects all the actions, leaving no room for confusion or implied dependencies.
Okay, so we need more descriptive function names, but what other strategies are there?
Well, we could use design principles to limit the side effects. Also, static analysis tools and thorough code reviews can spot these unexpected behaviors.
So, what can we learn from this example?
Always be mindful of hidden side effects. Explicit is better than implicit. Don't assume a function only does what its name says.
Got it. Thanks, Robert. So, in short, when it comes to writing clean code, it's always crucial to make sure that the name of the function correctly and comprehensively describes all actions it does.
Absolutely, Andrew, good summary.
Thanks for this. Hey, Robert, let's talk about this output argument thing. It seems like a simple concept, but are there specific downsides we should be aware of?
Yeah, absolutely. Imagine you have a function to format a report. If you use an output argument, the function might modify some variable outside its scope. That can be tricky to track.
So, it's like passing a ball back and forth. Not ideal.
Exactly. You're changing state outside of where that function is supposed to be responsible. Think of it like an accountant who does a calculation and puts the answer on a slip of paper somewhere else. Messy, right?
Okay, so like if you had a report object, the function could directly update the report's data, right? Makes more sense.
Absolutely. It's more encapsulated. The append footer example I gave before, you just call it on the object directly, and it takes care of the details within the object. Much cleaner.
So, are there any situations where using an output argument might be okay?
In very specific circumstances, like extreme performance needs for instance, you might see slight speed differences. But generally, in most applications, the clear and maintainable object-oriented approach is the way to go.
Interesting. So, you're saying for most of the cases we work with, there are few good reasons for using them?
Correct. The benefits of encapsulation are usually greater in terms of maintainability and understanding the code.
Thanks, Robert. That clarifies things. Hey, Robert, I was looking at some code the other day, and this function just, well, it was confusing. It did this thing, but also returned a value. You know?
Yeah, that's a classic problem. It sounds like a violation of command-query separation.
Command-query separation? What's that?
It's a principle in software design that says a function should either change the state of something, a command, or it should return information about something, a query, but not both.
Okay, so if a function is doing both, it's confusing?
Exactly. Imagine a function called set that sets an attribute and returns true if successful. That's a command and query hybrid. You end up with code that's hard to read and reason about, like if set username Uncle Bob. Is that checking if it was set, or if it got successfully set?
Right, that's super ambiguous.
Yes. Better to separate it, like set attribute, username, Uncle Bob, if successful, or return a boolean with attribute exists, username before the setting. It's much clearer that way.
So, we should always separate them?
Not always, there are exceptions, but separating them is the general rule. It helps to understand the actual intent of the code much better.
What are some real-world examples of where this is really important?
Databases. Update commands are separate from query commands to retrieve information. Data validation, too. One function checks if the data is correct, and another function then stores the data if valid, preventing errors and increasing consistency.
I see. So it's not just about avoiding confusion, but also about preventing bugs?
Exactly. It improves maintainability, too. If you have to change the behavior of the attribute setting, you only have to change one piece of code, not two.
That makes total sense. Thanks, Robert.
You're welcome, Andrew. Any other questions?
No, I think I got it. Thanks again. Okay, Robert, you're saying functions should ideally just do one thing. But, error handling feels like a whole different thing, right?
Exactly. It's a separate concern. Think of it like this. A function to calculate the area of a circle shouldn't also be checking if the user entered a valid radius or handle network issues.
So, you're saying the try/catch blocks should be right at the top? That sounds a bit unusual.
Precisely. It's about keeping the function focused. If the try block is at the top, that immediately tells you the function's purpose, and the try handles any problems related to just this function itself, and only that function. Think, what is this single function meant to do?
But what if the function is doing something that might fail, like querying a database? Doesn't that require checking for errors?
Yes, and the database query itself should be in a separate function. If there's an error, the error handling logic should be local to that database query.
Right? So, maybe you want a function to be more like a wrapper?
Exactly. You're abstracting the process. The core function handles the logic, and the try/catch/finally block handles the errors without affecting the core.
So you don't use a try/catch inside a loop or complex calculations?
Not usually. Try/catch should encompass the smallest scope of actions. Consider the database connection separate from other calculations.
Got it. Makes sense. That way, you isolate the source of the error for better diagnosis.
Precisely.
Wow, clear. Thanks. Hey, Robert, thanks for joining us. We've been talking about clean code, and error handling always seems tricky.
Absolutely. It's a frequent source of frustration for developers.
Can you explain the dependency magnet problem with error enums?
Sure. Imagine an enum for all your error codes. Every class that needs to check for errors needs to import this enum. If you add a new error, every class needs to be recompiled. That's a major pain.
So, recompilation is a significant hurdle?
Exactly. It slows down development and deployment. It's like a snowball effect.
So what's the alternative?
Exceptions. You create a base exception class, and then you create new exception types as needed. Those new exceptions are simply new types derived from the base. That avoids the recompilation.
Aha! So new errors don't impact old code.
Exactly. The open/closed principle helps here. Your code is open for adding more errors but closed to modifying existing code.
How does that impact maintenance?
It's much easier to maintain. Adding new errors is straightforward without affecting the rest of the codebase.
So, exceptions win?
It depends. Sometimes, for performance-sensitive applications, using enums might be better. But, for general-purpose apps, exceptions usually win out.
You mentioned the open/closed principle. Can you elaborate?
It's about designing software to be easily extended without modifying existing code.
That sounds great. So, Robert, what's your rule of thumb? Exceptions?
Generally, yes. But analyze the use case.
Perfect. Let's move on.
Right.
Thanks again. Hey Robert, great to have you back. We were talking about writing clean code, and you mentioned the dry principle. Can you give us some more context about when this principle really shines?
Absolutely. Dry, or don't repeat yourself, is a cornerstone of clean code. Imagine code with identical blocks repeated 4 times. Maintenance becomes a nightmare. Change one section, and remember to change all 4 instances. It's a recipe for errors, and makes the code harder to understand and maintain.
Right, it's kind of like having 4 separate recipes for the same dish. That sounds tedious. So, what are the key benefits to using dry?
Readability and maintainability are massive gains. We avoid redundancy, making the code far easier to understand. Plus, fewer lines means less chance for errors. And when a change is needed, you only need to adjust the original code once, which is crucial.
So, how do we know when code is truly duplicated?
It depends. Some repeating is okay for clarity. But if a block of code does the exact same thing 4 times, that's a good candidate to dry up. It's less about repeated than whether the code serves the same function across 4 areas.
Interesting. So, are there any situations where maybe repeating code is actually helpful or even necessary?
Sometimes, doing so might improve clarity in the short term. However, when you're building larger programs with large teams, the dry principle becomes way more important to ensure code maintainability across different modules, or by different members on the team.
So you're saying to dry it up unless there's a compelling reason not to, right?
Precisely. It's not an absolute rule. It's like choosing between a hammer and a scalpel. You may use the hammer in a pinch, but the scalpel is often more precise.
Thanks, Robert. This is very insightful.
Thanks for having me, Andrew.
You're welcome. Hey, Robert. Thanks for joining us today. We're diving into clean code, and structured programming seems central. What are your thoughts on Dijkstra's rules?
Well, Dijkstra's structured programming is a great guideline, Andrew. It encourages a predictable code flow, making code easier to read and maintain.
But the piece I'm struggling with is this idea of function size. Is there a magic number?
Not really. It's more about complexity. For very small, straightforward functions, a few break or continue statements aren't a problem.
So, like if I have a function that just checks if a number is even.
Exactly. You wouldn't need the complexity of structured programming. It's about the logic, not the line count. You know, cleanliness comes from a balance of structure and utility.
A great example. Can you think of cases where goto might actually be useful?
Sometimes, in exceptionally complex logic where you need to jump out of many nested loops, it can be more efficient than multiple conditional statements. But you're right, it's mostly bad practice and readability suffers.
So, is there a risk that adhering too strongly to structured programming might lead to less efficient code?
Potentially, in small functions. It's the trade-off I've been mentioning. Readability and maintainability might take precedence over micro-optimizations in many scenarios.
I see. It's like choosing the right tool for the job. So for large projects?
Absolutely. Structured programming really shines. It drastically reduces bugs and errors.
So, is there a particular situation where structured programming is almost required?
Safety-critical systems are a prime example. Where errors are potentially catastrophic, clean, predictable code becomes essential.
That makes a lot of sense. You're making it all clear.
Glad to help.
Thanks, Robert. So, Robert, you're saying writing a function is like writing a paper? You start with a rough draft, then polish it?
Exactly. It's rarely perfect from the get-go. My first drafts, they're often long-nested with weird names.
Lots of indents, right? And probably a lot of duplicated code?
Absolutely. But, I have a suite of unit tests. They act as a safety net.
So, you're changing the code with those tests acting as the guide?
Yeah. I use the tests to drive the changes, basically. I split out functions, rename variables, and generally clean up to get the code how I want.
Okay, so you keep the test green throughout the whole process?
Exactly. If a test breaks, I know I've messed something up, and I have to fix it.
What about refactoring and reorganizing? You mentioned shrinking methods. How do you know when a function has gotten too big?
It's often a combination of things. A function becomes unwieldy if it's doing too much. Sometimes it's just the length of the argument list. Lots of indenting or nesting often suggests the function is doing too much.
So a clean function is a short, focused one?
It's about doing one thing well. One function does one thing. A function that's doing multiple things is probably best broken up into smaller, separate ones.
That makes sense. But what if, the structure changes a bit? Does that create risk that tests will break?
It's tricky. If you're changing a function in a way that impacts how other parts of the system work, you really need to know what's going on. Good unit tests are important for helping to identify those problems early.
So you're saying good tests help to identify the need to break down functions?
Precisely. A failing test often highlights an area that needs more granular functions.
Fascinating. Thanks, Robert. Robert, you were talking about clean code earlier. Now it seems you're emphasizing something called domain-specific languages. Can you explain how this fits in?
Sure, Andrew. Think of a system as a story. You wouldn't tell a story using just English. You'd use a specific language, right? Well, programming is similar.
Okay, but how? How does that make our code better?
A domain-specific language, DSL, is a specialized set of rules and functions tailor-made to a particular task or domain. Instead of using a general-purpose language, like Java or Python, you create one that's better for your specific task. Imagine a language designed only for financial modeling. It'd have commands for specific financial operations, making that code easier to read and write.
So, functions and classes are the equivalent of the verbs and nouns in this specialized language?
Exactly. The code becomes a specialized, readable language focused on that system's needs.
So, this code example you showed is
a great illustration of a DSL. The setup tear-down includer uses functions to assemble the components of a page in a specific way. You see how specific the tasks are? This helps to create a clear, structured story.
I see. So, if I write code in this style, what's the big advantage?
Well-defined DSLs are easier to maintain and extend because the language is tailored to the problem. Less chance of making errors and easier for others to understand.
That's interesting. Does it always mean more maintainable code, though?
Not always. It depends on the design and the complexity of the DSL, and how much you adapt to the code to maintain it.
Aha, I see. So it's a specialized language tailored to its task and could be more maintainable, but there's a caveat?
Exactly. You need to carefully consider your trade-offs. We have to weigh benefits against potential challenges.
That makes a lot of sense.